Okay, so maybe you've heard of this famous storm. This is Jupiter's Great Red Spot. It's a centuries-old storm that is larger than the Earth. Now, this is a good reminder that when we get to the more distant planets in our solar system, the scale sort of starts to become unfathomable. Just beyond Mars, we have a planet that is 2.5 times more massive than the rest of the planets in our solar system combined. That is Jupiter. Now, Jupiter tends to get a lot of hype for this. People really like that it's sort of the king of the planets. But mystery is also directly proportional to how far away we get from Earth. So, while there's this crazy storm on the surface of Jupiter, that's just the beginning. So Jupiter is where this incredible scale and mystery begins, but that's only the beginning. I'm here to tell you that right next door there is something unfathomable. The Great Red Spot is cool, but there is a hexagon on the North Pole of Saturn, and nobody's talking about it. We need to talk about this. What's going on? This shit's crazy. Like, what? How is there a hexagon on the North Pole of Saturn? That doesn't make any sense. Okay, so to understand why, we must begin with a story. The year is 1977, and NASA has just sent the twin Voyager probes to go fly by Jupiter and Saturn and eventually explore the ice giants and beyond into interstellar space. Now, this was groundbreaking because it was the first time we ever had received detailed images and data from the outer planets. They had essentially been a mystery up until that point. Now, upon getting the first Voyager images of Saturn, imagine their surprise when NASA planetary scientists saw straight lines. Long straight lines don't tend to exist in space or anywhere in nature, really. Thus, Saturn's hexagon was discovered in 1980 thanks to Voyager 1 and Voyager 2. But it was just discovered, not really explained. The Voyager trajectories had their eyes set on interstellar space, so they provided a glimpse but no complete image of the hexagon. They couldn't just do a U-turn and check out something weird that they saw. What NASA could tell us was that it's big. The hexagon is twice as wide as the Earth, and it would be decades before we knew more, but eventually we got a closer look thanks to the Cassini space probe launched in 1997. It was functional from 2004 until 2017, when it ran out of fuel and launched itself into Saturn's atmosphere to burn up. They didn't want to risk harming any of Saturn's moons, I guess, but planetary science is just kind of metal like that. Now, in 2006, Saturn's North Pole was in winter, so we couldn't view it in optical light. It was dark, just like winter at the North Pole on Earth. But winter on Saturn lasts for many Earth years, so we really needed to just be patient. In the meantime, we could observe it using Cassini's visual and infrared mapping spectrometer. Now, this is essentially a camera that's viewing in infrared light. This is heat. So because it was viewed in predominantly infrared light, it was visually quite haunting, to say the least. And it doesn't look like what it would actually look like with our eyes if we were to take a look at Saturn's North Pole. But in 2009, Saturn's spring equinox arrived, so Cassini could finally use its optical imaging science subsystem to view the hexagon as we would see it with our eyeballs. This first clear view showed a hexagon-shaped jet stream that was 30,000 kilometers across, going 500 kilometers per hour, all around a polar vortex that spins around Saturn's North Pole. Now, that's a lot of big words that I'll get back to in a minute, but first, some conversion out of metric for our viewers in the States, Liberia, Myanmar, and literally nowhere else. That's 20,000 miles across, spinning 300 miles per hour, for those who prefer needlessly confusing measuring systems. Anyways, doing some very rough back-of-the-napkin math, this hexagon, if we were to scale it down to the size of Earth, would be the size of Australia. So that provides some relative scale for what we're dealing with here. Now, just a moment ago, I mentioned two things, polar vortex and jet stream. Earth also has a polar vortex, just like Saturn. It's essentially a moving ring of air around the North Pole. Now, we experience cold surges here on Earth thanks to the polar vortex, so maybe you've heard it discussed on like weather channels and things like that. But a jet stream, on the other hand, is a narrow band of strong wind in the upper parts of an atmosphere, like a stream, but fast like a jet, I guess, and air, not water. Anyways, it doesn't matter. Jet stream, fast-moving path of air in the upper atmosphere. On Earth, our jet streams are chaotic, but the jet stream on Saturn is completely symmetrical. Why? Well, a better question is, why don't we have symmetrical jet streams on Earth? Now, weather and wind patterns on Earth come from the sun, essentially, just like everything else. The wind is essentially caused by uneven heating of the Earth's surface. It flows from areas of high pressure to low pressure, but its path is disturbed by Earth's geology, high mountains and low valleys that penetrate into a rather thin atmosphere. If Earth were a perfect sphere, it would look quite different, but it's not. Saturn is homogeneous in comparison, with no clear surface to speak of. It's just a ball of gas. It has a core, but this definition of core is fuzzy at best. Saturn is what's called a gas giant. Now, this isn't a misnomer, it's just a nomer, I guess, because it advertises exactly what it is. It is a gaseous giant. It's a giant made out of gas. So to understand why Saturn is fundamentally so different from Earth, for example, we need to zoom out and consider the entire solar system. Okay, so we're gonna need to change setting for this one. You may want to sit down for this. I have a little plant companion with me. Anyway, welcome to the crash course in solar system formation and dynamics. Yeah, I told you you'd want to sit down for this. Essentially, at the center of our solar system today is our sun, right? Which accounts for more than 99.86% of the mass of the entire solar system. Jupiter makes up the other 0.1% or so. The other 7 planets make up the remaining tiny percentage. When considering all of the planets at once, there's a clear divide between the inner 4 and the outer 4. The Fantastic Four is something else. The inner 4 planets are terrestrial. That is, they're made of rock and we can stand on them. Whereas the other outer 4 planets are gas and ice giants. They may have solid or liquid cores, but not in the way that we really think about it. It's kind of a fuzzy definition. So how did this division come to be? Well, when the sun was forming some 4.5 billion years ago, it had a disk of gas and dust orbiting around it called the circumstellar disk. Astronomers don't get too creative with their names. They either go all out or they kind of get lazy with it. The planets essentially clumped together out of this disk and cleared out the rest of the gas and dust. This disk was not exactly uniform because of an invisible line. This is where things get a little bit weird. The line that divides the terrestrials from the gas giants is called the frost line. This line profoundly impacted how the planets formed because it represented the distance far enough away from the sun where temperatures are so low that volatiles such as water, methane, and ammonia can condense into ice. Any closer and the volatiles vaporize. This means that water and other ices exist in larger quantities in the more distant parts of the solar system. More ice meant larger cores that could then pull in more gas, leading to the massive gas giants of the outer solar system. In comparison, the inner solar system can't have volatiles in those same quantities because they vaporize. Thus, the inner 4 planets are made of rock and metal, things that could condense in the hotter setting of the inner solar system. The frost line is where this division comes from, and this line lives on today within the asteroid belt between Mars and Jupiter. Okay, now we can take a breath. Solar system formation is sick, but hard to explain. It's pretty wild, actually. Solar system dynamics is where it's at. That shit's fun. That shit's really fun. I need some more tea. Okay, we're done. So this is why Earth is so different from Saturn. It's a rock with a bit of atmosphere rather than the other way around. Earth's atmospheric chaos is caused by the large geological features that protrude into a rather thin atmosphere. Without those protrusions, Saturn is easily able to produce symmetrical shapes within its atmosphere. It's just a spinning ball of gas, which is essentially a symmetrical system. This situation makes it relatively easy to produce something called standing waves. This is essentially a wave shape that doesn't appear to move. It's easy enough to do this that we've actually reproduced it in a lab and have been able to make loads of different shapes by changing certain variables. This was done by Oxford University in 2010. Now, this happens on Saturn because of a difference in speed between the jet stream and the rotation of Saturn itself. So Saturn is rotating just like Earth is rotating, and then remember the jet stream is just that fast-moving stream of gas in the upper atmosphere. So Saturn's northernmost jet stream, the one that's producing the hexagon, just so happens to be spinning at a speed relative to Saturn's spin that it's conducive to producing that shape. If it were going at a different speed relative to Saturn's spin, it might produce a different polygon shape, and we've reproduced that in the lab setting. So although planetary scientists are still working to uncover exactly what's going on with Saturn's hexagon, it's not a complete mystery anymore. So there you have it, I guess. Astrophysics attention tends to be cluttered with news of black holes and gravitational waves and supernovae, because those are the things that win Nobel Prizes. But while these are exciting things, some of the most mind-blowing space science can be found in a perfect hexagon right next door, only 1.5 billion kilometers away. That's a mere stone's throw, astrophysically speaking. That's 950 million miles. Or about this many Ford F-150s.